Hello friends, in this video lecture we are going to learn how to model the speed governing system of a alternator. So let us begin. So friends, in our previous lecture we have discussed the speed governing mechanism for an alternator. So today we will learn how to model this speed governing mechanism. So before we proceed, let us consider that the power system is initially operating under steady condition, where these linkage mechanisms are stationary, the pilot valves are closed, and this steam valve setting is opened by some definite value, allowing some definite amount of steam to pass. With that, the speed of the alternator is fixed. Okay, so this condition, let us characterize it as, first let us characterize the frequency. F naught, I'm denoting it as, okay, so it will be system frequency, or we can also call it as speed, because we know that speed and frequency are having direct relationship. Then output of the alternator, okay, or turbine output, I can call turbine output, which is equal to generator output when it is possible, when we neglect the generator losses. Next, you see, we have considered that the steam valve setting is opened by some definite value. So definitely this point E on the linkage mechanism will be at some fixed position. So let us characterize that position as well. So that YE naught, it will be steam valve setting. Steam valve settings. Okay, see, we have all why I'm writing here why, that already I have given you, told you yesterday. Why will be taking as movement of this linkage mechanisms, and specifically the downward direction movement will be considered as a positive one. Okay, now in this system, what we will do is we will give a command. Okay, what command we are going to give here is, let us use this speed changer. Now if I want to raise the speed, so what I have to do is I have to lower this lever. Okay, when I'm going to lower this lever, what happens, the point A on this linkage will move downward. Okay, as it moves downward, the point C, because point B is fixed. Okay, it is a fixed link. It is a link. ABC is a single link which is fixed at point B. So as it is fixed, we can imagine that this point C will move upward. So as this point C is moving upward, which will let this point E to move downward. So because of this, what happened, the settings, this gate to the steam will open further. So resulting into the rate of steam will increase here. Okay, as more steam is we are allowing to pass, the turbine speed will increase. Okay, as the turbine speed is increasing, definitely turbine output will increase, and corresponding there will be a increase in the output of the generator. Okay, so what how we can write over here as this this change in position of A, this change in A position is, it is resulting into corresponding change in output power. Okay, so as it is correspondingly, so we'll put some proportionality constant here, and it is PC, change in power output. Now particularly I'm mentioning it as PC because it is a commanded input we are giving. So what we can write here as delta PC is commanded change or commanded increase in power, commanded increase in generator output, we can say. Okay, now what happened, because of this command will set into a sequence of motions. Okay, or it will enable the motion of sequence of events. Okay, see what is happening here. Because of this movement of A, some more movements will be there. So the first movement, what we can say is, it is here. As the point A is moving downward, the point C is moving upward. Okay. So now we will use here a basic mechanics to understand the relationship between the movement of point A and point C. Okay. Now already we have considered that downward movement will be the positive movement. As this link ABC is fixed at point B, so if suppose if A is moving, it will move in this rotational. Okay, it can move in this rotational manner. Okay, respectively, correspondingly, this point C will also move in this rotational manner uh, till the point where this point B is fixed. Okay, so what how I can write over here as, with the help of that basics of mechanics, I can write it as change in position of A. Okay, it will be multiplied with this L2. Now I'm writing plus. See, you can see here the movement of A is downward, so that's why we have taken positive. Again, the movement of C, it looks like upward, but as I said, as the point B is fixed, so it will be in a rotational way. Okay, so with that, it will be in the same direction. So that is why we'll take plus here only. So plus YC into L1, that is equal to 0. Okay, so this change in position of C, it is because of change in position of A. So I need to get this change in position of C in terms of this change in A. So I can write it as change in position of C, it will be equal to, you see here, it will be just equal to L2 by L1 into change in position of A. Okay, now let us call this as equation number 1 and this to be equation number 2. Okay, so with the help of that equation number 1 and 2, can I write it as the change in position of YC, or the change in position of C, it will be, see this minus L2 by L1, let us denote it with some constant minus K1. Okay, and this change in YA, with the help of that equation number 1, can I write here as Kc into delta Pc. Okay, see here, this delta Pc is nothing but delta Ye only. Why it is so? Because you see, because we are, if we are going to move this linkage on this point A downward, correspondingly there is a downward movement of point E, and in proportion to that only the power will change. In proportional to that only power will increase. So that is why that delta Pc, we can consider it as same as change in position of this point E as well. Okay, so now consider this as equation number 3. Now what happens, as the output is increases or the speed of the alternator is increases, this speed governor, it is installed at the shaft of the alternator. So what happens, as the speed is increasing, this fly valve will move outward. Because of that, what is happening, the point B on this linkage mechanism will move downward. Okay, why it is moving downward? Because there is an increase in the speed. So as there is an increase in the speed, I can say that there is an increase in the frequency. So the downward movement of point B, it is in proportional to the change in the frequency. So I can write over here as the motion of YB, it is because of proportional change in frequency. Okay, and we have to give some proportionality constant. Let us give it as k2 dash. Okay, so let us call it as equation number 4. Furthermore, you see here, as this point B is moving downward, as this B is moving downward, it will move this point C downward as well. Because of this point B is moving downward, this point C will move downward. So point C, downward movement of point C, it is because of the downward movement of point B. So let us see how we can relate it. To relate that, I'll draw that linkage mechanism separately here. Okay. this is A, this is B, this is C. See now, we are considering the effect of downward moment of C with respect to downward moment of B. Now in this, the point A is fixed, it is not moving. The point A, it is fixed, it is not moving. So how I can get that downward moment of C? Downward moment of C, it will be, see these are L1, L2. Okay, so the downward moment of C, it will be in multiplication with this L1, okay, minus, see again now here, uh, see if it is A and C, then we can say rotational moment we can consider, but as it is B and C, so there will not be a rotational moment, so we'll get here minus only, so delta YB will get here. But you see, as point A is fixed, so that moment of point B will affect the link A, L1 and L2. So here we'll get L1 plus L2. See, this is the basics of mechanics. So from that I'm writing here. So with this, can I write the delta YC as L1 plus L2 divided by L1, that L1 I'll shift here, into, see, delta YB we get here. Okay, let us call this as equation number 5. Now with the help of equation number 4 and 5, can I write it as delta YC is equal to, okay, so for this, let us give some proportionality constant. Okay, definitely we'll get some proportionality constant. Of course, one more proportionality constant will come with that delta YB, that is K2 dash. So this constant and that constant together will write K2 into change in frequency, K2 into change in frequency, call this as equation number 6. Okay, so you see here, resultant movement of C, it can be written as, we have to sum these two equations, equation number 3 and equation number 4. So the net movement of point C, I'll write here, net movement of point C, we get here delta YC as per the equation number 3, it is minus K1 KC into del PC, minus K1 KC del PC, and this is plus K2 del F. Call this as equation number 7. Okay, now similarly, because of that, the point D will also move. Okay, so the movement on of point D, it is contributed by movement of point C and movement of point E. It can be written as, now I'm directly writing here. Okay, so the movement of D, so let us write it as delta YD, okay, is equal to, it will be L4 divided by L3 plus L4 into delta YC plus L3 divided by L3 plus L4 into delta YE. All this as equation number 8. Okay, now I can replace this length or the linkages with some constant. So let us replace it. So we get delta YD as K3 delta YC plus K4 delta YE. All this as equation number 9. Okay, now what happens as this point D is moving? Okay, suppose what happens here, as this point, suppose if it moves downward, okay, if it moves downward, what happens, this high pressure oil will enter here, and it will enter to this chamber through this valve opening. So it will push this main piston upward. Okay, it will push this main piston upward. What will happen because of that, uh, the steam input will get reduced, and there is a corresponding reduce in the speed of the turbine. Okay, so now the movement of this point D, for this movement, let us define some justifiable assumptions. Okay, let us define some justifiable assumptions. So let me give that justifiable assumptions. So the first assumption is that, say, definitely this piston, this main piston will have some inertia. Okay, when the high pressure oil it comes and when it exert some force on that main piston, definitely it will oppose it with the help of that inertia of that main piston. So let us assume that here the pressure of the oil is very high as compared to the inertia of this main piston. So we are going to neglect that inertia of the main piston in this condition. Okay, again the second one assumption is that the amount of oil entering into this cylinder is proportional to the time for which this uh, pilot valves are opening. Okay, so now see what happens. This movement of point D, if it is moving upward or downward, correspondingly it will directly affect the position of point E. As I said, the movement of point D is resulting into movement of point E. So that movement of point E, I can write it as movement of point E, I can write it as with some proportionality constant K5. See, it is because of the point E will move upward or downward in proportional to the this pilot valve opening time. Okay, so the time for which it is open, this valve will move with that proportional. Okay, so now for to get that we have to use the integration here, because we have to apply the time integral, because it is depending on the valve opening time, so that we can model it in mathematics as with the help of time integration. Okay, so let us suppose that the valve is open from the time 0 to k. Okay, and in that the movement of the point D, now I'm writing it as negative of yd. Why I'm writing is it as negative, let me explain you here. See, the downward movement of point D, if I suppose the downward movement of point D, it will be positive. Definitely it will be positive. But you see, when it moves downward, it will push this point E upward. So here there is opposite directions. So definitely if the point D is moving downward, so definitely point E should move upward. So the effect here, the movement of point E is upward. So we should get a negative movement here. So to get that, to get a moment negative result for this point E, I'm putting here negative sign. Okay, so now what we will do is we will convert these variables into a Laplace domain. We'll take a Laplace of that. Okay, so let us take, first we'll take for this equation number 7, then we'll take the Laplace of this equation number 9, and then we will take the Laplace of this equation number 10. Okay, first let us take for equation number 9. So it will result delta yc of s will be equal to, see, Laplace, constant of Laplace, no change, constant will remain as it is, minus k1 kc. Okay, so it will become delta pc of s here, plus k2 will remain as it is, delta fs. Okay, this is the Laplace of equation number 7. Call this as equation number 11. Now Laplace of equation number 9, we'll take the Laplace of equation number 9. If for equation number 9 it will become yd of s is equal to k3 yc of s plus k4 ye of s. Okay, call this as equation number 12. Now Laplace of that equation number 10, it will be ye of s is equal to that k5. We know the Laplace of that integration is 1 by s. Okay, so that minus sign I'll put here, that 1 by s into this Laplace of this del yd of s. Okay, so we have taken the Laplace transformation. Now what I want is, I wanted to eliminate this yc. Okay, so how we can eliminate that, let us see. Because I want the result in terms of ye of s with respect to change in frequency. Okay, so how we can do that, let us see. First, what I will do with the help of that equation number 11 and 12, see, in equation number 12 this term is there, delta yc of s, and it is nothing but it is equal to equation number 11. So I'll put that equation here. Okay, so that delta yc of s, this term will be eliminated, so we get delta yd of s. For this we'll get some term here. Okay, if I put this delta yd of s in this equation, so that delta yd of s will get eliminated here. Okay, if you do that, at the end you will get this result, you will get this equation, delta ye of s is equal to k1 k3 kc delta pc of s minus k2 k3 delta f of s divided by k4 plus s by k5. Okay, so you will get this term. Okay, now what we will do is we will rearrange this term and let us write it as delta ye of s is equal to delta pc of s minus 1 by r delta fs, okay, into ksg divided by 1 plus tsg into s. You should get this equation. Now here these terms, r is nothing but speed regulation of the governor, ksg is the gain of this speed governor, and tsg is the time constant of this speed governor. Okay, I'll write these terms here separately. R is equal to k1 kc divided by k2, and it is called as speed regulation of the governor. Next, that ksg, it is k1 k3 kc upon gain of speed governor, and that tsg is nothing but 1 upon k4 by k5, and it is called as time constant of speed governor. Okay, so you see here what uh, what equation we have get. What is the meaning of this equation? See, this is del ye of s. It is nothing but the change in the position of e, or we can say it is a wall setting. Okay, it is because of the commanded power, or it is either because of the change in frequency. Okay, so wall setting changes, it will be either because of change in commanded power, okay, or change in the frequency. Okay, so how we can draw the block diagram for this equation? So that block diagram is here. I'll explain you that block diagram, because in order to learn the whole uh, load frequency controlling for a single area, we need to get the block diagram of individual responses, and at the end we have to club all of them to understand the response of the load frequency control for a single area. Okay, so with the help of that equation, I'll get that equation here downward. Okay, because referring to that equation, we can understand. In reference to this equation, it will be easy to understand. See now, leave these terms that we will think of this KSG divided by 1 plus TSG into S later on. See, this is the output. The steam wall setting is the output. So this output is equal to, it is here. Okay, it is the summation of the commanded power and the change in frequency. Okay, see, the commanded change in power is here. Now this change in frequency, we are taking it as a feedback. Okay, as we are placing that speed governor on the shaft of the alternator, so that changes in the speed it will sense and it will give us the feedback, and it is giving feedback in multiplication with the speed regulation of that speed governor. Okay, so this is positive signal, this is the negative signal, and the summation of these two signal is now getting multiplied with this gain and the time constants. So we are getting this output here. Okay, so this is how we have to model the turbine speed governor system. Okay, in next lecture we will learn how to model the turbine. Okay, thank you very much.